Hi everyone, I am Dr.S.Anbuselvi, Associate Professor, PG and Research Department of Chemistry, Sri Sharda College for Women, Salem. I am going to discuss about carboxylic acids. Carboxylic acid are organic compounds containing carboxyl groups. In this, carbonyl group and hydroxyl group combine together to form a carboxyl group so-called carboxylic acid. Now let us see the classification of carboxylic acid. Based on the nature of R group, we can classify the carboxylic acid into aliphatic carboxylic acid, aromatic carboxylic acid and alicyclic carboxylic acid. In aliphatic carboxylic acid, the R group is an aliphatic group. Say for example, R may be methyl group, ethyl group, etc. In aromatic carboxylic acid, the R group may be benzene, phenol, like that. In alicyclic carboxyl group, the R group should be an alicyclic one. Now let us see the second classification. The second classification based on number of carboxyl group. If the number of carboxyl group present in a compound is 1, then the compound is said to be monocarboxylic acid. If the number of carboxylic acid is 2, means it is dicarboxylic acid. If the number of carboxyl group present in a compound is 3, means it is tricarboxylic acid, and so on. Third classification based on the functional group or the number of double bonds. According to the nature of functional group or number of double bonds, the carboxylic acid is classified into 3 types: saturated carboxylic acid, unsaturated carboxylic acid and substituted carboxylic acid. In saturated carboxylic acid, there is no carbon-carbon double bond. Example for saturated carboxylic acid is acetic acid. In unsaturated carboxylic acid, there is carbon-carbon double bond. Example for this unsaturated carboxylic acid is crotonic acid. And in substituted carboxylic acid, the substituent may be hydroxyl group, amino group or halo group. Example, lactic acid. In lactic acid, the substituent is OH group. In aminoacetic acid, the substituent is NH2 group. In chloroacetic acid, the substituent is Cl group. These are all various monocarboxylic acid, dicarboxylic acid, tricarboxylic acid. Acetic acid is a monocarboxylic acid. There is no carbon-carbon double bond. Therefore, it is saturated monocarboxylic acid. Whereas in cinnamic acid, there is one carbon-carbon double bond. So, it is unsaturated monocarboxylic acid. Here, the substituent, the R group attached to the COH group is an aliphatic group, that is CH3 group. Therefore, it is acetic acid. Similarly, If the R group attached with COH group is a aromatic group, that is benzene ring, it is aromatic carboxylic acid, and this one is alicyclic carboxylic acid. Similarly, there are so many dicarboxylic acid, oxalic, malonic acid, succinic acid, adipic acid, phthalic acid, in which there are two carboxyl group. Similarly, there are so many tricarboxylic acid too. Example for which is citric acid. Citric acid contains 3 carboxyl group. Similarly, these are all some other examples of monocarboxylic acid. Now let us see preparation of carboxylic acid. Oxidation of primary alcohols or aldehydes. Primary alcohols as well as aldehydes can undergo oxidation reaction to form corresponding carboxylic acid with the help of oxidizing agents such as acidic potassium permanganate, potassium dichromate, nitric acid, Jones reagent, Tollens reagent, and manganese dioxide. The aldehyde can also be oxidized to acid in presence of mild oxidizing agents such as Tollens reagent and manganese dioxide. Preparation of carboxylic acid from alkyl benzene. The aromatic carboxylic acid preparation is possible through the oxidation of alkyl benzene. Next preparative method is hydrolysis of cyanide, nitriles, amides. Nitrile undergo hydrolysis to form amide. The amide in presence of catalyst form carboxylic acid. The amide can also undergo hydrolysis in presence of acid or base, give the carboxylic acid. Next method of preparation is from ester. The acidic hydrolysis of ester leads to the formation of carboxylic acid. This reaction is carried out in the presence of acid or alkali. Next is the preparation of carboxylic acid through haloform reaction. This reaction serves to oxidize specifically a methyl ketone to a carboxylic acid containing one carbon atom less than the parent ketone. When a methyl ketone is halogenated, in basic solution, the halogen replaces all three alpha hydrogen atom. Halogen replaces all the three alpha hydrogen atom. This trihaloketone reacts further, resulting in the cleavage of CC bond. After acidification, the carboxylic acid and haloform, that is trihalomethane, are formed. Then we see the general chemical properties of carboxylic acid. First one is acidic character. You know well, there is a relation between acidic character and Ka as well as pKa value. If Ka is greater, the acid is strong. You know well, the Ka the pKa is the negative logarithm of Ka. The higher the Ka value, the lower will be the pKa value. That is, for stronger acid, Ka is high and pKa is low. Similarly, for weaker acid, Ka is low and pKa is high. Here in this table, few carboxylic acid and the corresponding pKa values are given. See here, this is formic acid whose pKa is 3.77 and this one is acetic acid whose pKa is 4.74. You know well, if pKa is low means it is more acidic. As per the concept of pKa, the formic acid is more acidic because it has lower pKa value than acetic acid. Similarly, monochloroacetic acid is less acidic whose pKa is 2.86 while comparing to dichloroacetic acid which has lower pKa value, that is 1.25, which in turn less acidic when comparing to trichloroacetic acid because its pKa is only 0.65. If pKa is low, then the acid is strong. The acidity of carboxylic acid is due to the resonance stabilization of its carboxylate anion. Resonance stabilization of its carboxylate anion. That is, the acidity of carboxylic acid depends upon the resonance nature of the carboxylate anion. Any factor which stabilizes the carboxylate anion more, which should increases the acidic strength. For example, here S is the electron releasing group. It increases the negative charge on the carboxylate anion and destabilize the carboxylate anion. Therefore, the acidity decreases. That is, electron releasing substituent decrease the acidic nature, whereas in this example the S is an electron withdrawing substituent which disperses the negative charge on the carboxylate anion, therefore stabilize the carboxylate anion and acidity increases. Collectively, we can say that electron releasing substituent decrease the acidic strength, electron withdrawing substituent increase the acidic strength. Till now, we have seen two concepts, two factors which affects the acidic strength. One is Ka and pKa, and the other one is electron releasing and electron withdrawing nature of the substituent. If pKa is low means Ka will be high, then the acid is strong. If pKa is high means the Ka value is low. If Ka value is low means then the acid is very weak. Not only the electron withdrawing and releasing nature, which is also related to the inductive effect, that is electron withdrawing and electron releasing nature of the substituent is somewhat related with the inductive effect of the substituent. Minus AF group that is electron withdrawing group increase the acidity of carboxylic acid. Say for example, trichloroacetic acid. In trichloroacetic acid there are 3 minus A effect chlorine atom. So definitely the strength of this trichloroacetic acid is more while comparing to dichloroacetic acid, because here only 2 minus A effect group only. Therefore, the acidic nature of the trichloro, dichloro, monochloro and acetic acid decreases in this manner. This is due to the minus A effect group. Similarly, in carboxylic acid, if a plus A effect group is present, then it decreases the acidic nature. Say for example, formic acid and acetic acid. In formic acid there is no plus A effect group, whereas in acetic acid there is CH3, which is a plus A effect group, which destabilizes the carboxylate anion. Therefore, the acetic acid is less acidic while compared to formic acid. Similarly, if the methyl substituent increases, then automatically the pKa value increases and the acid strength decreases. In addition to the electron withdrawing and electron releasing nature, electronegativity also influences the acidity of carboxylic acid, which means if a substituent is lower electronegativity group, which means it has lower minus A effect, then the carboxylic acid is less acidic. The electronegativity of various halogens decreases in this manner. Similarly, if electronegativity value decreases, automatically the minus A effect decreases and acidic strength also decreases. Among fluoroacetic acid and iodoacetic acid, fluorine is the most electronegative atom and iodine is the least electronegative atom. Therefore, fluoroacetic acid has more minus A effect, more electron withdrawing effect while comparing to iodine. Therefore, fluoroacetic acid is the stronger acid while comparing to iodoacetic acid. The acidic strength also depends upon the distance between the carboxyl group and the substituent. You know well, the inductive effect decreases with distance. That is, if the chain length increases, automatically the inductive effect decreases. If the negative effect, minus effect decreases, the acidity also decreases. For example, the acidity of the following chlorobutyric acid decreases in the following manner. Among these 4 chlorobutyric acid, alpha chlorobutyric acid is the strongest acid. Why? Because in alpha chlorobutyric acid, the COH and Cl group are nearer to each other. So, minus effect of chlorine is very high, which easily stabilizes the carboxylate anion, therefore more acidic. But in delta chlorobutyric acid, the chain length is high, so the inductive effect, minus effect is very less, therefore it is less acidic. Among various dicarboxylic acids, say for example oxalic acid, malonic acid, succinic acid, glutaric acid, adipic acid. In oxalic acid, the distance between the electron withdrawing COH group and the another carboxylic acid group is less. So minus effect nature in oxalic acid is greater while comparing to adipic acid. Therefore, oxalic acid is the strongest acid while compared to adipic acid. Now let us see the acidity of maleic and fumaric acid. Generally, the maleic acid and fumaric acid are the stronger acid while comparing to the acidic nature of the corresponding saturated analog, that is succinic acid. While coming to maleic acid, during the first ionization, because of the intermolecular hydrogen bonding, the carboxylate anion is more stable. So, for first ionization, the Ka value for maleic acid will be high, whereas in fumaric acid, during the first ionization, because the two COH group are trans to each other, such a kind of intramolecular hydrogen bonding is absent. Therefore, the first ionization process have low Ka value. While coming to the second step, second ionization process, it is very difficult to cleave a hydrogen atom, second proton, from a stable hydrogen bonded intermediate. Therefore, in maleic acid, the second ionization process is very slow and the Ka value for the removal of second proton is less when comparing to fumaric acid. In fumaric acid, since the two carboxylic acid group are trans to each other, the formation of dianion occur in an easy manner. Therefore, while considering the first ionization process, malic acid is a stronger acid while comparing to fumaric acid. During the second proton removal, the Ka value for fumaric acid second ionization is greater than malic acid second. Therefore, malic acid is stronger for first ionization but weaker for the second ionization while comparing to fumaric acid. So, in this video, we have seen what is carboxylic acid, how they are classified, and what are the preparation of carboxylic acid. Then the chemical property of carboxylic acid, that is effect of substituent on the strength of carboxylic acid, are covered. Thank you all.